Okay, in this next video, we're looking at proportions. And you might say, well, what is a proportion? Well, in terms of what is a proportion, it's really more important of what it allows us to do. So it kind of plays off that idea of ratios that we looked at before. So what does a proportion allow us to do? It helps us determine, or we could say it determines equivalent ratios that are proportional to the original. Okay, so it determines equivalent ratios that are proportional to the original. For instance, maybe you're looking at this example here, and it says you are trying to mix water with your favorite sports drink powder. Okay, so usually you have some kind of container of powder, and it would come with a scoop, and you'd scoop out the powder and mix it with water, right? Well, oftentimes the package might say, in this case, like in this example, what the ratio of cups to scoops of powder should be. In this case, it says, the package says to use 2 to 3. So the ratio is 2 to 3 of water to powder ratio, okay? So for every 2 cups of water, we want 3 scoops of powder. However, you and a bunch of friends are coming over, okay? So you have some friends coming over, and you decide, no, I want to use 10 cups of water, okay? Well, that's where these proportions come in. If you want to use 10 cups of water, then we need to know how many scoops of the powder we need, okay? Now, the way we can set this up, just like this says 2 to 3, remember, we can represent a ratio as a fraction, and that's what this is saying here. So if we have 2 to 3, or what we're really saying is 2 cups for every 3 scoops. Okay, so 2 cups of water for every 3 scoops of powder. Now, you're wanting to use 10 cups. So what we're going to do is we're going to set this equal to a fraction. Okay, so 2 to 3, set that equal to a fraction where we have 10 cups per the unknown. That's what we're trying to find, an X number of scoops. Okay, well, how am I going to be able to solve that? Well, think about it in terms of how do you clear fractions when we're solving things algebraically? Well, if I wanted to get rid of division by 3, we could multiply by 3 to both sides, right? We'd multiply 3 to both sides. This would go away, and I'd get 2 equals 10 times 3 is what? 30 over x. Well, then how do I clear that fraction? Well, I'd have to multiply by x, right? So we'd multiply by x, and we get 2x equals 30. Okay, well, I'm getting close to what I want. This is kind of where I'm at now. How do I get rid of that 2? Divide by 2 to both sides, okay? So I'm actually going to work on the example I was working on. Divide by 2 to both sides, and we get x equals 15, just like they have here. So in other words, if I'm going to use 10 cups of water, I need 15 scoops of powder, okay? That is an equivalent ratio. 2 to 3 is equivalent to 10 to 15, okay? They're proportional ratios. That's called cross-multiplying, okay? So what we just did there, that's called cross-multiplying. For instance, 1/3 is equivalent to 5 over 15. Now, how you tell if a fraction or ratio is proportional, in other words, they're equivalent, is when we multiply across. That's why it's called cross-multiplying. 1 times 15 and 3 times 5, and as long as they come out to equal the same thing, we're okay. That's what they're showing here. 1 times 15, 5 times 3. Well, 1 times 15 and 5 times 3, we'd have 3 times 5 over here is equal to 1 times 15. Now, if they're proportional, if those fractions, those ratios are equivalent, they should come out to be the same. What's 3 times 5? 15. What's 1 times 15? 15. So 1/3 and 5/15 are equivalent fractions or equivalent ratios, okay? That's where the cross-multiplying comes in. And so that's what it says here. For any numbers A and C and any non-zero numbers B and D, if we have the ratios or the fractions A over B and C over D, those two are equal. Those two are equal if and only if A times D equals B times C, okay? Just like up here, okay? These two fractions were equal because when we cross-multiplied, we got the same number on both sides, okay? So that's what that's saying there. And we can use that to our advantage. We can use that to find a missing piece, just like in our example with the cups of water and the scoops of powder, or we can use it to determine if two fractions are proportional. For instance, if we wanted to determine if a ratio of 3 to 4 is equivalent to 7 to 9, we can set those up as fractions, 3 over 4 and 7 over 9, and cross multiply. If they're proportional, if they're equivalent ratios, we should get the same thing on both sides. So we'd have 3 times 9 and 4 times 7. Okay, well, what's 3 times 9? 27. What's 4 times 7? 28. Is that the same thing on both sides? No. So these are not, these are not proportional. However, we could also look at the example of 1.5 to 2 and 13.5 to 18. If we wanted to see if those are proportional, again, we could set it up as fractions, 1.5 over 2 and 13.5 over 18, and then cross multiply. 1.5 times 18, 2 times 13.5, and see if those are equal. 1.5 times 18, what does that come out to be? 27. 2 times 13 and a half, 27. Are those two sides the same? Yes. So those ratios are equivalent. Those ratios are proportional. Okay? Now, we can use that to our advantage to help us find a missing piece of the fraction or a missing piece of the ratio, or in some cases, if we have an example like this, maybe we could solve for x. Okay, now this says what would be the value of x? Well, we can use our cross multiplication to find x. 3 times 10, or excuse me, 3x times 10, okay, then 24 times 5. Then we would just multiply. 3x times 10 is 30x. 24 times 5 is 120. Well, I have 30 times x. How do I get x by itself? Divide by 30, right? If I divide by 30, I get x equals 4. So x equals 4 would make these guys proportional, and that's what they're checking here. If I plug this back in for the x, it should come out to be a proportional fraction. 3 times 4 would give me 12 over 24. Okay, are these guys proportional? Yeah, 12 over 24 is 1/2, and 5 over 10 is 1/2. Okay, so we have equivalent ratios. Same thing with this example here. If we're trying to solve for x, we can cross multiply 5 times x plus 2. Now, this is going to be times the whole thing, so we can think of it in terms of a parentheses. 5 times x plus 2, the whole thing, is equal to 15 times 6. Well, if we apply the distributive property here, we would get 5 times x is 5x, 5 times 2 is 10, and 15 times 6 is 90. Two-step equation, subtract 10 from both sides, and we get 80. Divide by 5 to both sides, and we get 16. So x equals 16. And again, we can plug it back in and check to make sure that we have proportional ratios, equivalent fractions. Okay? So that's dealing with it algebraically. Now, other examples we might run into are some actual real-world examples. We can apply this to real-world examples just like we did with the cups of water and the scoops of powder. Example 1 says the ratio of boys to girls in a class is 4 to 3. What does that mean? Well, it means for every 4 boys, okay, there are 3 girls. Okay, so if we take the classroom for every 4 boys, there's going to be 3 girls. But they say if there are 20 boys in total in class, how many girls are there going to be? Okay, now we can set this up as a ratio just like they do there. We can say boys to girls, okay, just like they show there. They said the ratio is 4 to 3. For every 4 boys, there are 3 girls. So boys to girls would be 4 over 3. Now, if I want to find girls, what we need to do is take that, our 4 over 3 here, and set that equal to what we know. We know there's a total of 20 boys. What we want to find is the girls. So that's what's coming up here, okay? So we have 4 boys. Let me just go back and backtrack here, okay? This is 4 boys for every 3 girls. But we know there's a total of 20 boys. What we want to find is the total number of girls, okay? In other words, we're looking for a proportional fraction, okay? Well, setting that equal, we could cross multiply 4 times g, okay, and then 3 times 20. We can solve for that. 4g stays the same, is equal to what? 60, okay? Then divide by 4, what are we going to get? Well, g is going to equal 15. So in other words, there are 15 girls in class. Well, that makes sense, okay? 4 over 3 is equivalent to 20 over 15. So for every 4 boys, there was 3 girls. In other words, if there's 20 boys in class, there's 15 girls in class, okay? So that's one example that we can apply that to. The next one is similar. It says the ratio of boys to girls is 1 to 3. In other words, for every 1 boy, there are 3 girls. Now this one's a little bit different. In the last example, they told us the number of boys and we had to find girls. This says the total number of students. So they don't tell us boys or girls, they just tell us the total number of students. Okay? Well, the best way we can think about this, if there are 1 boy for every 3 girls, so there's 1 boy for every 3 girls here, then the total number of parts, if we're thinking about the total number of students, the whole would be 4 parts, okay? So 1 boy would be 1 part out of the whole, 3 girls would be 3 parts out of the whole, so the whole would be 4. There are 4 parts in total, okay? So we can think of this in terms of 1 boy to 4 parts, the whole classroom, or 3 girls to 4 parts, the whole classroom. So for every 1 boy out of the total of 4 parts, there are 3 girls out of the total of 4 parts, okay? So we can represent not just part to part, 1 girl to 3, or 1 boy to 3 girls, but we can represent it as parts. There is 1 boy out of the total of 4 parts. There are 3 girls out of the total of 4 parts. Or you can think of if I just grabbed 4 students, 1 boy, 3 girls, that'd be a total of 4 students there, okay? So 1 part out of the whole and 3 parts out of the whole. So that's kind of what we're going to use here. Now they want to know the number of girls. So one method that we can use is take the girls ratio out of the total. Well, for every 3 girls out of the total of 4 parts, we know there are 28 students. Okay, so this is what they have going on here. For every 3 girls out of the total of 4 parts here, we know that there is a total of 28 students. That's what they tell us over here, is that there's a total of 28 students. So we want to find the equivalent ratio that tells us the number of girls per 28 students. Well, that's multiplication, right? So we have our 3/4 to g over 28, 3 times 28, and 4 times g. So we have 4g equals 3 times 28. Okay, well, solving for this, we have 4g equals, what's 3 times 28? 84. Divide by 4, and we get g equals 21. So there are 21 girls in class. Okay, what does that mean in terms of how many boys there are? Well, just take 28 minus 21, so boys would be 7. Okay, that makes sense. 7 out of the total of 28, that guy right there, that would be what? 1 out of the 4. That's what we said in terms of parts. It'd be 1 boy out of the whole of 4. Okay? And then this says I have 21 girls out of the total of 28, which is equivalent to our ratio of 3 girls out of the whole. So this would be 3 over 4. Okay? So it's useful sometimes to represent ratios not just as part to part, but sometimes part to whole. Okay? Another method we could use if we're going part to part. So if we're going for boys, every 1 boy for every 1 boy there are 3 girls, then we have to represent the total, and we have to represent the boys from our total, and we have to represent the girl, or we could represent the girls from our total, just depending on what we're looking for. In this case, it says we're trying to find girls, right? So we're trying to find girls by the second method. Now, if I just let G be for girls, that's what we're trying to look for, and I know there are 28 students, then how many boys are there? Well, it'd be 28 minus the girls, right? If I take 28 minus the number of girls I have, isn't that the boys? So that's what this is saying here. If there's one boy for every 3 girls, then an equivalent ratio for boys to girls would be 28 minus the number of girls would be B, boys, all over the total number of girls. Well, that's like what we solved before. We can solve this guy. Okay, 1 times G, and then 3 times 28 minus G. Well, this would just be the distributive property there. Okay, so applying the distributive property there, we have 3 times 28, 1G equals 84 minus 3G. Well, if I add 3G over, we get 4G equals 84. Divide, and we still get the number of girls is going to be 21. So we're still going to get the same answer that the number of girls is 21. Another way we can do it, and this is another way that might come up. In this example here, they say 1x plus 3x equals 28, okay? Well, remember, for every 1 boy, there were 3 girls. So if we think of this in terms of x being the number of boys, okay, then girls would be 3 times as much. Then 3x would be the number of girls. So this is just another way to solve the same question. If x is the number of boys, then the girls would be 3 times as much, so it would be 3x. So in other words, if I take the number of boys plus the number of girls, we know that there's a total of 28 students. Well, I can solve for that. 1x plus 3x is what? 4x. Divide by 4, and we get x equals what? 7. Now, that's the number of boys. How do I find the number of girls? Well, if I plug that back in here, 3 times 7 is what? 21. So in all three different ways, we found that there are 21 girls, okay? So there are multiple ways to work the same question, okay? Let's look at example 3 here. It says, a triangle has angles in the ratio of 1 to 2 to 3. What is the size of each angle, okay? So all that's saying here, again, this is in terms of part to part to part. So this represents the ratio of the 3 angles. However, if we think of it as parts of a whole, how many parts do I have here? 1 plus 2 plus 3 is what? 6. So there are 6 parts. So in this example, it's probably going to be better to think of it as parts of a whole. So in terms of the first angle, that the ratio would be 1 to 6. For the second angle, it'd be 2 to 6. And for the third angle, it'd be 3 to 6. That's probably going to be the easiest way to work through this, is think about the measurements in terms of parts of a whole. So for every 1 measurement here, it'd be 6 for the whole. Or 2 measurements, it'd be 6 total. And then 3 measurements, it'd be 6 total. So this represents each angle out of the total or out of the whole. Okay. Now, the reason why that is useful for us, if we just take the first one, let's just focus on the first one here. So on the first angle, we said it's 1 part to each 6 parts. If I think of a triangle, let's say I had a triangle where this is x, y, and z. Well, let's try to make this a little bit better. Maybe we can write it out to the side here. If I take a triangle, let's say the first angle is x, the second angle is y, and the third angle is z. What we're saying is, let's say the smallest angle we're focusing on, okay, that measurement is 1 to every 6, then we can set up a proportional ratio to find what the measurement of x is. Remember, each angle of a triangle adds up to be what? 180. So what we're trying to find is an equivalent ratio that says this angle is going to be 1/6 of the total when we add it together. In other words, x out of 180 has to equal our 1 part to every 6, okay? So in other words, we can take our smallest angle, x, out of 180, and what we're trying to find is, what is the measurement of x that would give me a ratio of 1/6, okay? Well, again, we could cross multiply and solve there. 1 times 180 gives me 180 is equal to 6x, okay, is equal to our 6x, which is kind of what they have over here. Well, if I divide that out, what am I going to get there? Well, I'm going to get 30, right? So if I divide that out, I'm going to get x equals 30, just like they have there. So my smallest angle is going to be 30. Then we can set up things similar for y and for z. Okay, so for y, it'd be 2 parts to every 6 equals y over 180. And for z, it'd be 3 parts to every 6 equals z over 180. And then cross multiplying, we would find that we would get 60 and we would get 90. Okay, so we'd have 30 degrees. Okay, so for x, we'd have 30 degrees. For y, we'd have 60 degrees. And for z, we'd have 90 degrees. And that should make sense. If you guys divide that out, the ratios would hold. 30 over 60 is 1 to 2. 60 over 90, we'd have our 2 to every 3, and so on. Okay, so the ratios hold true. So that's one way to solve it, and usually that's going to be the easiest way. Another way we could do it is kind of like we did before on the second method. If we think of x as the measurement of the smallest angle, then y, let's just think of this as x plus y plus z. All those angles have to add to be 180, right? So if we think of x as the smallest measure, then y would be twice as large, and z would be 3 times as large. That's what the ratio said, right? Twice as large and 3 times as large. So we can think of it as 1x plus 2x plus 3x. 1 part plus the 2 parts x plus 3 parts x equals 180. Well, again, we would solve and we get 6x equals 180. Divide by 6 and we get x equals 30. So we would still get the same answers. X would be 30, then twice as large would be 60, and 3 times as large would be 90. Okay, so we get the same answers there. So there are different ways we can work that question. Now, the last example we're going to look at here is example 4 that says, what are the possible names for a quadrilateral that has the ratio, the proportion here, the ratio of 3 to 1 to 3 to 1? Okay, well, what do you notice about that? That's the ratio of the sides, right? So if it's 3 to 1, 3 to 1, what does that mean? Well, it means 2 of the sides have the same length and the other 2 sides have the same length. What geometric figures do you know of where we have 4 sides that 2 of the side lengths are the same and the opposite 2 side lengths are the same? Well, for one, it could be a quadrilateral, anything that has 4 sides, right? So we're talking about a quadrilateral with 4 sides. Well, that would leave us with a rectangle. Okay, we could have a rectangle where this side length and this side length are the same, and this side length and this side length are the same. Or we could be talking about a parallelogram, okay, where this side length is the same, this side length is the same, and these two are the same, okay? So that would be 2 different answers that could possibly be representing what we're talking about there. Okay, so that's what this question says. What are the possible names for the quadrilateral? Well, it could be a rectangle, it could be a parallelogram, where 2 sides are the same and then the 2 opposite sides are the same. Okay, so then we'll work on these questions together in class and hopefully it'll start to click and make more sense.